everybody. Happy Friday. I wanted to, I was going over your homeworks and assessments and things like that, and just came up with some other things that I wanted to make really clear for you guys and to kind of help you make sense of all of these series convergence tests. There's a lot. In fact, this is one of the handouts, and I just wanted to show you that I put this together. I'm not gonna go over this really. But I did want to point out the fact, however, that this one also includes the telescoping, which we haven't done in a long time, but is definitely part of one of the series tests that we can use. And it also includes the root test, which, remember, the root test is not required, but it is something you're allowed to use. And if you count all of them, there is a total of 10 tests. So that's a lot to remember and a lot to keep straight. So I would spend a good amount of time kind of like looking over this and reviewing it. And then the one piece that I did want to kind of point out is just a reminder that when you're using the divergence test, it doesn't show convergent. It only tells you if it's divergent under this condition. So it doesn't give you any other information than that. So now that we're done with that clarification, we're going to move on to the series tips and tricks, part 2. So this is the second tips and tricks kind of document that I put together for you. So the first thing I wanted to talk about, and this is super important, I'm noticing people are really confused about the definition of when a series converges and diverges. So the definition is based on the sequence of partial sums, S sub n, which is a sequence, right? Which means that this is S sub 1, S sub 2, S sub 3, and so on, right? So if the sequence of partial sums, if you send n to infinity and take the limit, if you get some number that's not infinity, then that tells you that the series diverges. Okay? I'm sorry, the series converges. And not only does it converge, but it converges to that exact value. And so what's important to note is that we're not saying that this is equal to this, right? That's not what we're saying. So you're not actually comparing series together. You're looking at the limit as n approaches infinity of that sequence of values, right? And we're trying to see what's going on with that. And so if that goes to a number, then that means that the series A sub n actually is going to be decreasing and is going to be like there's going to be a number that's going to it's going to stop at, and so it can be decreasing and heading in. I'm not sure if I'm explaining that well. But in any case, I apologize if I'm not. If you're still confused, please ask me about it in office hours or something, or shoot me an email so I know, and I'll try and help. But just keep in mind that these two are directly related. And so anytime you have a question that deals with sequence of partial sums, it is related to the definition. And so by definition, the limit as n approaches infinity of S sub n is equal to the convergence or divergence of that series, A sub n, right? Because remember, S sub 1 is like A sub 1, and S sub 2 is A sub 1 plus A sub 2, like that. So we're looking at this series here, or that sequence here, as we go down to the bottom and sending that to infinity. So we're trying to see, if I'm going to keep on adding up the terms of my series over and over and over again, going all the way out to infinity, that, as I do that, if that diverges, then definitely the series itself is going to diverge. If it goes to a number, that means that, eventually that sum is going to stop somewhere, okay? And so that's why we can use this. So that's the definition. So you need to make sure you have this down because it is the definition. All right, and then the next thing I wanted to talk about is some clarification on absolute versus conditional convergence. So the thing to keep in mind is that for absolute convergence, right, basically if you have that the converges, then you have absolute convergence. Because if its absolute value converges, then the one without the absolute value will definitely converge. Okay? So if you have the absolute value of a series, and you can show that that's divergent or convergent, then you've got absolute convergence. Now, if you have a series where its absolute value diverges, then that's the situation where it's conditionally convergent. So, for instance, the P series, right, 1 over n. We know that this diverges, right? But negative 1 to the n of 1 over n actually converges. And so this is a situation where this series right here is conditionally convergent because this one converges, but its absolute value doesn't. If we take away the negative, the plus or minus 1, then the absolute value is not going to diverge. So that's a conditionally convergent situation. All right, and then here's some, some more information that you can use that I put together for to kind of help you understand error bound, and then there's the root test, and here's the correction right there. And I'll let you read through those. So what I wanted to spend a good amount of time on is this right here. So how to decide which convergence test to use. So this is kind of a strategy checklist. You can go in the book. There should be a strategy checklist in the textbook. Every textbook kind of has something along those lines, and a lot of them say a lot of the same kinds of things. But this is kind of like a good checklist to keep in mind. Again, remember that there's multiple tests that work for different series. So there's not just like one answer, like, okay, anytime I see a series like this, I can only use this particular test. That it just doesn't work that way for the most part. So these are kind of like the things that you can think through as you're trying to decide which is the best test to use. So I recommend always trying the divergence test first. And the reason is that a lot of times you can just kind of like eyeball it. You can kind of look at the a sub n, and you can see if that looks like it's something where the limit is going to not equal 0. Because if the limit equals 0, then that doesn't help us. So all you're really looking for is kind of eyeballing it to say like, hey, does it look like the limit's going to equal something other than 0? And if you're not sure, then it's worth going ahead and kind of like, you might have to do L'Hopital's or something like that. So it's worth maybe trying that. But a lot of times you can just kind of like, you can kind of see it. And then if you end up having to kind of like, if it's too much of a bear of a problem, obviously, where you're going to be using L'Hopital's like multiple times or something, you might want to try something else, because then you don't want to get stuck in like, the limit hole. All right. So that's the first thing I recommend you try. And then after that, so remember we talked about the other day in class that you can use the best test to use when when the alternating series test doesn't work is the divergence test. And that's because if I as n approaches infinity of a sub n, actually, here, let's say it this way, of negative 1 to the n times a sub n. That's no different than just kind of saying what's the limit as n approaches infinity of negative 1, of just a to the n, or a sub n, if the limit doesn't equal 0, right? And so it's really easy. If the limit doesn't equal 0, then they're not going to be both of those are going to give us divergence. If it diverges without the plus or minus 1, it's definitely going to diverge with it. So you can just omit the negative 1 to the n, and then you can go ahead and use the divergence. But if that doesn't work, then of course, if it's alternating, then you want to use the alternating series test. And it's important, I kind of put this like a sub n should be able to be written as negative 1 to some power with n, like n plus 1 or n minus 1 or something along those lines. As long as it makes it go back and forth, so it's just every other term is positive and every other term is negative. Number 3, and this is really important piece of information to talk about, and that is series? If so, you're going to use one of those. So what I mean by that, because that's super, super, super important, is that if it's not exactly like a p-series or not exactly like a geometric series, then you don't use those. Okay? So, like for instance, I'm just going to kind of make something off the top of my head. So say we have like, I don't know, 2 to the n plus 1 over 4t, right? So that is very much like a geometric series. In fact, and as we go out to infinity, that plus 1 just becomes insignificant. So it really is a lot like this, right? Well, and we know that that is 1 half to the n, right? And so we know that that's a geometric series, but this is not a geometric series. This is. This is not. Not a geometric series. Yes, a geometric series. So this isn't geometric, so you can't use the geometric series test on something like this. What you can use is the geometric series test. You can like use this piece of information and then try one of the comparison tests. So either the limit comparison or the direct comparison. Okay? Same thing with p-series. If you have something like, and I actually say this in line, say this up here somewhere too. Oh, no, maybe it's down there. Anyway, if you have something like, I don't know, 9/10, I don't know, n squared. Let's say that. Right, now this, I can pull that 9/10 out, and now when I look at it, I have exactly a p-series. Not close to a p-series, exactly a p-series. And so this one I can use for a p-series. But if it was something like, you know, 9/10 times n squared minus 1, or minus 10 not a p-series anymore. Okay? Now, it can be similar to a p-series, right? It is similar to this one. And we can use it in that way. We can, we can go, oh, okay, it's similar to this. But in order to be able to apply that information, we need a comparison test again. So with the p-series and the geometric, unless it's exactly one of those, like if I can write out the terms and I get like 1 over n and then, or 1 over n squared and, each time, or I get, 2/3, I'm multiplying by 2/3 every time, then it's geometric. Then it's p-series. But if it's not exactly like that, if I were to write these terms out, if I plug in 1, I get 2 plus 1 over 4. I don't know why I did it that way. And then if I plug in 2, I'm going to get 5 over 16, right? And then if I plug in 3, I'm going to get 8, 9 over, 64? So clearly, I'm not able to multiply by the same number every time, right? So it's not geometric, and you can't use the geometric series test. All right, I hope I made that clear. Let's move on. Don't forget the telescoping series, right? So if you can rewrite it as, separating it into 2 fractions, 2 linear terms, then it's really helpful to use as the telescoping series. And then number 5, if the series is similar to the p-series or geometric, that's when you use the direct or limit comparison test. So that's kind of what I was talking about. That kind of goes with 3. The other time that a lot of we like to use the limit comparison test or the direct comparison test is if we have expressions, some kind of a rational expression where there's polynomials or roots of polynomials. It's very common that people like to use the direct or limit comparison tests for those kinds of situations. Now, again, that's not the only option, obviously, but that is where you kind of like your mind kind of goes initially, because that does tend to work out to be the easiest way to prove things like that, whether or not they converge or diverge. Moving on to number 7, does a series include factorials or powers of n? So factorials, ratio test every time. Powers of n as well. You can use the root test with this information up here with factorials, but I like to do the canceling, the ratio test. I personally like to use the ratio test if I have a choice between the two, because it happens to not be the one that, is on the exam. So the root test is something that we use most of the time because it can take something and make it a lot easier for us to solve really quickly, whereas all the other tests will be much more long and involved. So there are situations where we do really want to use the root test primarily, and that's in this next step. So you really want to use it when you have something like constants, right, to the nth power, or where the series can be written, the whole series can be written to the power of n, or something like that, where you can take the nth power and it really gives you something that's really helpful. That's when you want to use the root test. Otherwise, the ratio test is usually the better choice. And then the last piece you'll notice, number 9, which is the last one I have there, that's when I bring in the integral test. And the reason I do that one at the end is because not only do you have to check that it's positive, continuous, and decreasing, so you have to state that every time and show that every time. Not necessarily show it at length, but if it's not obvious, you might have to write 1 or 2 things, to show that it's clear that it's positive, continuous, and decreasing. But that's important, and if you don't have that, you won't be able to use the test technically, actually. And you will definitely lose points on the AP exam if you don't incorporate checking those things. So you have 3 criteria that you have to deal with, and on top of it, the integral of all of the tests. The integral test is the one that is the longest and the most involved, and it's the last one that I want to have to use. And keep in mind too that integration is one of my favorite things of all time in math. So I love solving integration problems, and I still don't want to use the integral test off the bat. All right, so those are kind of like a list of things to check. And then some other thoughts that I wanted to say. So first, and this is really important, you guys, so write out the first few terms of the sequence, of the series, if you don't know what's going on with it, right? If you're not absolutely positive you know exactly what it looks like, write out a couple terms. And I keep saying this because I keep seeing people making these mistakes. I keep getting, work and assessments and homeworks and stuff like that back, where I'm seeing people not realizing that it's actually like a nice, easy geometric series, or it's actually kind of like a nice, like if you were to write out the few terms, it would turn into this really nice, easy series to figure out. And a lot of people, I keep seeing it over and over again, that people aren't seeing that because they're not writing out the terms. They're just immediately jumping into okay, what test should I use? Instead of really wrapping their heads around what's going on with the series. And so that's really important. And hopefully I don't have to keep saying it for much longer, but I'm going to keep saying it until I stop seeing that on your papers. So, all right. Couple other comments about some of these other tests. The geometric series test, this is just kind of reiterating what I was saying above. And I kind of like the way that this is phrased. Looking for a fixed ratio, right? So fixed ratio, this is definitely a fixed ratio. That's not. And so you can tell you're always looking for this fixed ratio here. So you're looking for this kind of a thing. And then if you don't know and you can't tell, write out a few terms. For P series, again, this is kind of what I was talking about earlier, where you can have something like 9/10 or 9/10n squared, right? Because you can pull out that 9/10, and now I have exactly a P series. So that's what this C means, that C, it could be like whatever constant you want that to be. All right. Moving on to some more discussion about direct versus limit comparison tests. And this is something actually that's come up a lot on the quizzes as I've graded them. The direct comparison test can only, can only be used when you show directly an inequality, right? You have to show either that, the test that you're using in your comparison is bigger than the test, series that you want to know whether or not it's convergent or divergent, right? That's for convergence. Or the test that you choose or the series that you choose has to be smaller if you want to show divergence. And you actually have to show the inequality. If you don't show that inequality, you can't use the direct comparison test. If you can't easily show that inequality, then don't use the direct comparison test. Use the limit comparison test. That's the fallback. If you're sitting there and it takes you like more than like 2 or 3 seconds to figure out whether or not you've got, you've got the inequality the right way, then move to the limit comparison test. It's more work. Like you don't have to, like with the direct comparison test, as soon as you show the comparison, you're pretty much done. So it is a little bit more work, but it's definitely worth it if you're having a hard time finding that comparison. And you will not get credit for using the direct comparison test if you don't show this exactly, or this one, of course. All right, and then also keep in mind that with the limit comparison test, you don't have to choose a series that's necessarily similar. So there was a problem that you had on the quiz actually, where it said, okay, we want to compare it to something like this, right? These two things here are not like I don't like the sine of 1 over n. How do I compare that? How do I know which one is bigger and which one is smaller and all that kind of stuff, right? There's not any nice way to get that 1 over n out of the parentheses and deal with it so that we can kind of like figure out what's going on with that. So there's no way of really showing the comparison to this. But it doesn't matter if you use the limit comparison test. It doesn't matter if 1 over n is slightly bigger, it doesn't matter. If you use the limit comparison test, it will always tell you that when the whatever series that you choose that you put in the denominator, right? So if that thing is convergent, then your series is going to be convergent. And if that thing is divergent, then your series is going to be divergent. And it'll always work out that way no matter what the sizes are like, no matter which one is bigger. So you don't have to do any comparison. You can just go ahead and just put them into the limit. And as long as it's something that is reasonable for you to find the limit with and like use L'Hopital's or something like that. So you do want to think about the kind of series that you're going to use to choose to compare, because something like, I don't know, 1 over e to the n is not necessarily going to be something that's going to be very helpful when we're computing the limit and using L'Hopital's rule. But 1 over n would be. So that's why that's a good one to choose. But that's why, so when we're talking about the limit comparison test, we don't have to worry about size so much. We're just trying to come up with something that, is going to show what we think should happen. Because remember, we always want to decide kind of ahead of time if we think it's going to converge or diverge, and then kind of choose our test and our series to use according to kind of like the assumption that we're making. So I hope that made sense. So in the end, use the limit comparison test if you can't actually show directly the inequality for the direct comparison. And then a couple things. The absolute versus conditional convergence. So I've actually tried making this video a couple times and had interruptions. So I can't remember if I said this to you guys or not above, or if I've just said it because I've tried to make this video multiple times. I don't know if you can hear one of the dogs like whining in the back room or in the bathroom or in the background. I had to kick her out because she was like making all sorts of noise in here. So hopefully it's not disturbing you guys. Anyway, so if I said this to you, I'm sorry for repeating myself, but absolute versus conditional convergence. So with the ratio and root tests, you always, always, always get absolute convergence. And the reason that you always get absolute convergence with the ratio and the root tests is because with the tests require you to put absolute value symbols around the series before you do anything. And so you're testing for the absolute value of that series when you use the ratio or root tests. So anytime you use one of those, you automatically get absolute convergence, assuming, of course, that your answer comes out to be convergent. So those are really nice. Those are good tests to use if the question asks like to show absolute whether or not a series is absolutely convergent. You can immediately jump into one of those and see if that works. And then the other thing that I wanted to talk about here is that when you've got like negative series, or you've got series that have like negative terms but aren't necessarily alternating back and forth, then the other time you want to try and think about absolute convergence is in this situation, because if you can put absolute value symbols around that series and then show that it converges, then you've been able to show that the series that you want, which would be the one without the absolute value symbols, right? You'd be able to show that that converges, and not only that, but it converges absolutely. And sometimes it's really hard to do it without sticking those absolute value symbols around it, right? So for instance, the best for sine and cosine, right, is this kind of absolute convergence idea, because both the sine and the cosine are less than or equal, the absolute values of the sine and the cosine are less than or equal to 1. And so you can very often come up with some kind of like a comparison test or something to like a really easy p-series because of that relationship. Now, if it doesn't work, if you end up like not getting what you're looking for, you end up getting divergence, then you might have to do something else. But that's oftentimes the best way to go. And then one other piece of information, and that is this: if you have like sine to the power of 1 over n, then, which is very similar to this one, right? So here we had sine to the first of 1 over n, and we wanted to compare it to 1 over n. And so if you have sine to the p of 1 over n, then you want to compare that to 1 over n to the p. So if this was sine squared, sine squared of 1 over n, then you would want to compare it to 1 over n squared. And if it was sine cubed, you want to compare it to 1 over n cubed, and so on and so forth. So that's just a little tip that I found. And then the last piece that I wanted to give you was this relationship here between like natural log and powers and factorials and stuff like that, so for help when you're thinking about comparison tests. So you'll note this relationship here, that the natural log of n is kind of like the smallest of all of them. And then, you know, you've got this hierarchy here. Now, this hierarchy is not necessarily true close to zero, like closer to 0. It's definitely true as we go out to infinity, but some of these things like trade places for a little bit until you get really far down towards infinity. But we're always going to infinity, so we can use the relationship that's really far down at the end. So those are the relationships that we can use. And then the last thing I wanted to talk about was I mentioned that I wanted to kind of go over this a little bit more. I think it was one of the classes asked some questions or something, and I didn't really have time that day to cover it, so I wanted to make sure that I did. And I thought this would be a great opportunity because I think it kind of follows with some of this as well. So I'm going to, just for ease of purposes, so that it's easy to kind of like read my writing and everything, because my natural log of n kind of like all looks like one, I don't know, squiggle sometimes. So I'm going to let n be x, and I'm going to use it that way so that there's not just a bunch of n's when I'm writing this stuff down. Okay, so when we're looking at this problem, the idea is we want to be able to, I think we actually, I don't even want, what do we do with that? Right? So I'm going to take the natural log, because remember I'm writing it as x to the power of the natural log of x. Like, what does that mean? What does that represent? Well, I can rewrite that as e to the natural log of that stuff. So the natural log of x to the power of the natural log of x. And then using the natural log rules, I can bring this down in front there. So then that's going to give me e to the natural log of x times the natural log of the natural log of x. And then this part right here is really x to the natural log of the natural log of x. Right. Okay, so this is where we're at now. So the question is, what do we do with that? And what does that represent? And so what we wanted to do was, what we're trying to do is we wanted to show that this converges. So we need a series to compare it to somehow, or to work with, that is something that we can use that shows that it's going to converge. And so we have 1 over something. So the first thing that we think of, right, is 1 over n. We know that one diverges. 1 over n squared, right, or 1 over n cubed or whatever. see if there's a relationship between, and of course we're dealing with x's in my example here. So let's see if there's a relationship that exists between like x squared and x to the power of natural log of x, right? So we want to see what kind of relationship exists here. And so when we're looking at this, and by the way, what we want is so we need, because we want to show that we have a convergent series, we need the series that we choose to compare it to be bigger, so that if the big series converges, that means the smaller series is going to converge too. So we need that this has that inequality, right? So that's what we need. And I'm showing all this work because this is required to show in order to use the direct comparison test, by the way. Okay? So what that means is we need the natural log, or x to the power of natural log of the natural log of x, to be greater than x squared, which means we need the natural log of the natural log of x to be greater than 2, right? So let's go ahead and solve that. If I solve that, I get e to the natural log of x greater than e squared, and that means the natural log of x is greater than e squared, and then if I just do the e thing again, I'm going to get x is greater than e to the power of e squared. And if you plug that into your calculator, you get approximately 1618. So I don't know if you guys remember about the lesson that day. I said it was some value like way out into the like 1500s or 1600s or something like that. I couldn't remember the exact value. So this is the value. So what this is basically saying, and I'll put the ends back into it, is that so because we know that 2, actually let's write it this way. We know that the natural log, my goodness, one more time. Third time's a charm. Is this my third time? I hope so. All right. We know that the natural log of, hold on, let me see what we got here. So we've got the natural log of n, and we know that that's equal to n, right? And that's coming from right here. So that's this equality right there. So we went from there to there. That's equal to n to the natural log of the natural log of n, right? And so, and I know that n to the natural log of n is actually greater than n squared. So then when I flip that over, let me say this. It's greater than n squared when n is greater than 1618, right? So then if I flip that over, I get 1 over n to the natural log of n is less than 1 over n squared. Now 1 over n squared is bigger, and it converges. So therefore, because this converges by the p-series, because it is a p-series, that implies by direct comparison that the other series converges, right? So our series converges by the direct comparison test using the p-series 1 over 2 to the n. All right, so there we go. I hope that made sense. I learned recently from grading some of my students' work that this line right here on the paper where I kind of drew that squiggly arrow, that when it gets sent out to you guys, that actually separates stuff quite a bit. So I wanted to make sure that it wasn't like messing up the copy that you look at later. All right, so I think that's everything with this. I'm going to make one other video where we're going to spend some time just going through a set of problems, a set of series to see if we can figure out the best test to use. So come on back for the next one.